Hi, I'm Dr. Shahriar Hossain. You are watching one of the video lectures of the Data Science lecture series on computingforall.com. Today, we will learn all about k-means clustering algorithm. Well, one cannot teach or learn all about a topic using one video, but I will provide as much details as I can regarding k-means clustering algorithm in this video. After going over this video lecture, you will have a good understanding about the algorithm, as well as you will know how you can apply k-means clustering algorithm on your own data tables using Python programming language. If you already know about k-means clustering algorithm very well, and if you are here just to check the Python code, then you can watch the last 13, 14, or maybe 15 minutes of this video where I explain a Python program that uses k-means clustering algorithm by leveraging the scikit-learn library. The k-means clustering algorithm is probably the most widely used clustering algorithm in data science. It is a partitional clustering algorithm. That is, it will divide the data space into k partitions. Points in each partition will form a cluster. Let us start by discussing what are the input and output of the k-means clustering algorithm. The input of the k-means clustering algorithm is the data and an integer number k, representing the expected number of clusters. The algorithm returns k groups of points from the data. That is, each data point is assigned a cluster ID out of k clusters. So if k is, let's say, 2, that means it is expected that the algorithm will give 2 clusters. Then the algorithm will take this data and it will assign a cluster ID to every row of this dataset. The output of the algorithm would be cluster IDs for all the rows. For example, maybe this row, this row, this row, this one, and this one will be assigned to cluster 1. And maybe this row, this row, this row, and this row will be assigned to cluster 2. In that case, these numbers associated with every row will become the output of the k-means clustering algorithm. The number of clusters k must be smaller than or equal to the number of points. For example, in this dataset we have 9 rows and number of expected clusters cannot be any more than 9. It makes sense, right? We cannot ask for 4 clusters when we have only 3 points. Similarly, we cannot ask for 15 clusters if we have 9 rows in our dataset. For this given dataset, we can ask the algorithm to give us 2 clusters, 3 clusters, so and so forth up to 9 clusters. If we ask for 9 clusters, then each point will become its own cluster. Again, for k-means clustering algorithm, we need 2 items. One is the data and the other one is k, the number of clusters. With our running example, if we plot all these points in a two-dimensional graph, we will see that these rows will be close by here. And the other points, which is 5, 4, 3, 4, 2, 5, and 1, 3 are here. We can see that there are 2 clusters. This is why I said that if we apply k-means clustering algorithm with k equals 2, probably these points will be in one cluster and the other points will go to another cluster. So we can say that this is cluster 1 and this is cluster 2. Definitely, we could call this one cluster 2 and this one cluster 1. It does not matter what we call each cluster. What matters is we have discovered the group of points in separate clusters. Now, why is the k-means clustering algorithm called k-means clustering? The k-means clustering algorithm creates k representations for k clusters. To create the representation of a cluster, the algorithm computes a point that is in the very middle of the cluster. For example, if you have these points in a cluster, then the very middle of the cluster will be, say, this one. As a result, this will be considered the representation of this particular cluster. Similarly, for another cluster, you will have another middle point, and that middle point will be considered the representation of the other cluster. Now, to compute a point that is in the very middle of a group of points, the algorithm takes the average of the points in the group. Soon we will talk about how to compute the average of a set of points. A synonym of the word average is mean. Since the algorithm deals with k clusters, it deals with k averages of the k groups of points, and hence the name of the algorithm became k-means. Each such mean or middle point is also known as the centroid or the center of a cluster. In this presentation, we will be using the word centroid as the representation of a cluster. That is, each cluster is represented by a centroid. Now, one might ask, why should we use a representation or a centroid for clustering data points? That is a valid question. Clustering is a combinatorial problem. We have data points. We want to find k groups of points in the dataset. We want to make sure that the points in a group are close by. That means we want to make sure that all the points in a cluster are locally in a neighborhood. Since clustering is a combinatorial problem and we do not know how to find the best cluster assignments, we will have to take all possible k groups from these data points and check which k groups have the best closest points. In each combination of points that form k groups, we will have to check the summation of distances between all possible pairs of points in each group. Going over all possible pairs of points in a cluster might, and in most datasets will, become computationally prohibitive. Also note that the number of combinations of assignments forming k groups is tremendously high. Therefore, it is hard to solve the clustering problem in a combinatorial way. What we do is we rely on k number of representations in the data space. It is easy to move the representations in the data space. Based on the distance between each point and k centroids, we assign cluster IDs to the points. Now notice that we are not giving cluster IDs based on combinations. Rather, cluster IDs are given based on the distance between each point and its closest centroid. The use of representations of centroids in k-means clustering algorithm makes the clustering problem feasible to solve. For our running example, maybe for cluster 1 the centroid will be around here, and for cluster 2 probably the centroid will be somewhere here. Let us discuss more about the concept of centroids. Given a group of points, a centroid is the center of the points. A centroid is computed by taking the average of all the values in each dimension of the data points in the group. For example, if we have a one-dimensional dataset in which we have 5, 10, 6, 9, and 10, then the centroid of this group of points will be the average of the points 5, 10, 6, 9, 10, which turns out to be 8. Hence, the middle point of all these numbers would be 8. Now let's go to our running example. Let us assume that this is our cluster assignment. Rows with the same cluster ID belongs to one cluster. In this example, we have two clusters, cluster 1 and cluster 2. Again, it is fine if we rename cluster 1 to cluster 2 and cluster 2 to cluster 1. These two sets of assignments are the same. We could even name the two clusters cluster A and cluster B. All that matters is if the points in the same cluster have the same cluster ID. Our dataset is a two-dimensional dataset. For now, let's say that this row belongs to cluster 2, 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 as well as this one belongs to cluster 2. We are going to find out the centroid of cluster 2. In the first dimension, which is feature 1, we have 9, then we have 11, then we have 10, then we have 12, then we have 11. In the second dimension of cluster 2, we have 11, 13, then we have 12, then we have 12, then we have 14. So in feature 1, we will take the average of all these numbers, and in feature 2 we'll take the average of all these numbers. If we take the average of all these numbers here, we get 9 plus 11 plus 10 plus 12 plus 11 divided by 5, which results in 53 divided by 5 equals 10.6. So the average in feature 1 for cluster 2 is 10.6. Now let's take a look at feature 2. The average of the numbers we have in feature 2 will be 11 plus 13 plus 12 plus 12 plus 14, which is 62 divided by 5, which results in 12.4. As a result, the centroid of cluster 2 will be considered as 10.6, 12.4. Let us erase everything from here because we will be now computing the centroid of cluster 1. To compute the centroid of cluster 1, we will have to take this row, this row, this row, and this row because they belong to cluster 1. To compute the average of feature 1, we will have to take the numbers 5, 3, 2, and 1. 5, 3, 2, and 1. To compute the average of feature 2, we'll have to take the numbers 4, 4, 5, and 3. 4, 4, 5, and 3. Then we'll compute the average. 5 plus 3 is 8, 8 plus 2 is 10, 10 plus 1 is 11. Therefore, the average will be 11 divided by 4 because there are 4 rows. 11 divided by 4 is 2.75. 4 plus 4 is 8, 8 plus 5 is 13, 13 plus 3 is 16. Therefore, the average is 16 divided by 4. We divide 16 by 4 because there are 4 numbers in feature 2. In cluster 1, the average becomes 4. Therefore, for cluster 1, the centroid is 2.75, 4. That means our representation for cluster 2 is this point, and our representation for cluster 1 is this point. Now let me ask you a question. If you have a d-dimensional dataset and you are trying to find k clusters, how many dimensions will each of the k centroids have? If your answer was D, then you are correct. That is, if you have a d-dimensional dataset and you are trying to find k clusters, each of the centroids will have d dimensions. That is, if you take the average of d dimensions, you will have d averages, and hence each centroid will have d dimensions. Please note that you computed average of every dimension of the points that belong to a cluster. Therefore, if your dataset is a two-dimensional dataset, then you will have a two-dimensional centroid. If your dataset is a three-dimensional dataset, then you will have a three-dimensional centroid. If your dataset has four dimensions or four features, then each of your centroids will have four features. If you have a 100-dimensional dataset, then each of your centroids will have 100 dimensions. For example, if you have this 5-dimensional dataset and if you have two clusters, and let's say that these rows belong to cluster 1 and these two rows belong to cluster 2, then you will have two cluster centroids, and each of those cluster centroids will be 5-dimensional. That is because you have 5 features in this dataset. I quickly showed the calculations, but I did not compute the fractions. So do the computation and you will understand how the cluster centroids are computed. Based on what we have discussed so far, given a set of cluster assignments, we can easily compute the centroids by taking the average of the points in the clusters. Another important aspect in k-means clustering algorithm is, given k centroids, we will be able to assign a cluster to each of the points. For example, we have these points, and let's say that two possible cluster centroids are provided. Now, if we ask the question for this particular point, which cluster centroid should this point be assigned to? Of course, this cluster centroid is closer to this given point than this cluster centroid. As a result, this point will be assigned to this cluster centroid. We can find out the distance between each point and these two centroids, and for each point we can say whether the point belongs to this centroid or this centroid. That's how we can provide a cluster assignment for every point given the centroids. Hence, there are two things to remember. Number one, given the data points that have the same cluster IDs, we can compute average of the data points to compute the centroid of the cluster. Number two, given centroids, we can assign a cluster for each point depending on which centroid is the closest to the point. K-means clustering algorithm starts by random assignments of cluster IDs to each point. Then it computes the cluster centroids for the assignments. Then it checks if the cluster assignments change based on how close the centroids are from each point. If cluster assignments change, then it recomputes the cluster centroids. Then it checks if it has a new set of assignments for the data points. The algorithm keeps repeating the process until it finds a situation where the cluster assignments are not changing anymore. Let us take a look at an example. In this dataset, let us assume that three clusters are randomly assigned first. The cluster assignments are marked by red, blue, and green colors. Now let's take the points that are marked by a red color. That means randomly these points are assigned in the same cluster. Now let's compute the middle point or the centroid of this cluster. And this cross point is the middle point, or this is the centroid of these points. Similarly, we will compute the centroid of the green points, and this is the centroid of the green points. And then we'll compute the centroid of the points that are marked in blue. Now all the clusters, red cluster, blue cluster, and green cluster, all these clusters have the centroids. These centroids are marked here. And when we have the centroids, we have to check whether for every point the cluster assignment remained the same as before. So let's take one point, such as this red point. The red point was in the cluster that had this particular centroid, but now we can see that the red point is closer to the green centroid. Therefore, we will change the assignment of this red point to green. Similarly, we will check the assignment of every point and we'll see which centroid it belongs to. After a reassignment of all the points, we find that these points are closer to this centroid and these points are closer to this centroid and these points are closer to this centroid. Therefore, using the new red points and the new blue points and the new green points, we recompute the centroids and we find that this is the centroid for the points that are marked in red. This is the centroid of the points that are marked in blue, and this is the centroid for the points that are marked in green. After we recompute the centroids, then it is time again to check the cluster assignments of each point. So what we do is we try to fix the cluster assignments, and we find that this point should be assigned to the centroid of the blue region or the blue cluster, and this is what we do. Then we find that this point is closer to the green centroid, so we assign this point to green. Now, since the cluster assignments have changed, we will have to try to recompute the cluster centroids. Since this is a new point that is added to the blue cluster, this blue centroid will move a little bit to this region, and since this point was added to the green cluster, so this centroid will move a little bit upward. And now we have another new set of centroids. So we'll have to check if the cluster assignments change. So we try to fix the cluster assignments, and we find that based on the distance from each point to all three centroids, we do not need to change the cluster assignments anymore. So that is when the algorithm realizes that the cluster assignments have converged to a stable situation. Therefore, the k-means algorithm will output this clustering result. That means for each of the points, it will assign a cluster ID. For example, if the cluster ID of the blue cluster is 1, then for each point in the blue region, the cluster assignments will be 1. For all the points in red region, if red is considered cluster 2, then for all those points, cluster assignments will be 2. Similarly, for all the points in the green cluster, if that green cluster is itemized as cluster 3, all those green points will be given a cluster ID of 3. So finally, k-means for k equals 3 for this particular data set will provide this clustering result. So we can say that these points are in one cluster, these points are in another cluster, and these points are in another cluster. Of course, in addition to cluster assignments for every data point, k-means will return the cluster centroids. So cluster centroids will become another output of the algorithm. In addition to that, also k-means clustering algorithm may return you sum of squared distance, which is basically the summation of all the distances from the points to their corresponding centroids. When we say sum of squared distance, it's not really the summation of all distances, rather summation of all squared distances. We'll talk about the summation of squared distances soon. In the previous video, we said that there are different types of clustering algorithms, one of which is partitional clustering algorithm. K-means is a partitional clustering algorithm, that is k-means divides the space into k parts, and this is how actually this algorithm divided the space of this particular dataset into 3 parts. K-means clustering algorithm is a local optimization algorithm. The overall k-means objective function, whatever the function is, finds out a local optimum. The algorithm is influenced by where it starts from. If the objective function is this one, for the initial set of centroids, if this is the starting point of the function, then it will try to find out the nearby optimum. The nearby minimum is here. It might not be able to find out the global minimum, which is here. If we start from here, we might find out a better minimum. If we start from here or here, we might be able to even find a better one. Sometimes people run the k-means clustering algorithm multiple times with random initialization with the hope that we might be able to find out a better local optimum. That's a valid approach. Many times in your dataset, if you have very good clusters, then we might always end up with the same local optimum no matter where we start from. But if our dataset does not have a good structure, or if our dataset have some sort of overlapping structures, there is a high chance that different starting points will take us to different local minimum. In some implementations of k-means clustering algorithm, there are already mechanisms to randomly restart the algorithm several times so that the best result is chosen from many different random initializations. Let us talk about the objective function that k-means algorithm minimizes. Although a K-means algorithm itself might not directly write this equation as a function of summations, but through the iterations of K-means, the algorithm eventually minimizes this function. Let us describe the notations first. K is the number of clusters. C varies from 1 to k. D is a data point or a vector in cluster C. Centroid C is the center of cluster C. These double bars indicate Euclidean distance. The square indicates that we are taking the square of the distance between a data point and a centroid. Now, let us talk about the objective function. The objective function here is based on cluster assignments. In any state of the running k-means algorithm, we will have all the data points. For every data point, we know in which cluster the data point belongs to, and we know the centroid of each cluster. The objective function is the squared distance between each data point and its assigned cluster centroid summed over all data points. Notice that we iterate over each cluster. Within each cluster, we iterate over each of the points or each of the vectors D in that cluster. That is, we are computing the squared distance between each data point and the centroid of the cluster the point is assigned to, summed over all data points. K-means clustering algorithm is a non-deterministic algorithm. That means if you run K-means algorithm for the same dataset with same number of clusters, you might not receive the same result. In different executions of the program, you might see different results, although most of the times for the same dataset, which has good inherent structure inside the data, you might see the same outcome, but the algorithm does not guarantee that you will see the same outcome all the times. Let me give you an example. Let's say that we have a two-dimensional space. That means we have a two-dimensional data set where actually we have these points. So let me draw the points. Now, if we run k-means clustering algorithm with k equals 2 in one execution, we might find that these points are grouped this way. In another execution, we might find that the points are grouped this way. That means in our dataset, we might have different structures, and k-means might give us those different structures. Also, k-means is a local optimization algorithm. That means that it is affected by its starting point. Remember that in k-means, we randomly assign clusters to all the points in the beginning of the algorithm. Based on what the random initialization is, we might see different results. For the same random initialization, we will probably see the same result all the times. But with different random initializations, we might not see the same result. That means k-means clustering is a non-deterministic algorithm. A non-deterministic algorithm is an algorithm for which, even for the same input, the algorithm might exhibit different behaviors on different executions of the program. In a deterministic algorithm, the corresponding program always gives the same output, which might not be the case for k-means clustering algorithm. Think about a scenario where you have a two-dimensional data set with a lot of random points. Now, if you apply k-means clustering algorithm with k equals 2, practically your centroids can be here and here, or Your centroids can be here, or your centroids can be here and here. For a lot of the initializations, k-means will have a lot of equally good alternatives. Basically, if we do not have clear clusters in our dataset, then the chances that we will receive different results for different execution of the program increase. In the previous example, we had very good structures in our data. That's why we were seeing two different results. Even with random points, we might see different results because k-means might not be able to improve over many iterations of the algorithm. With random points, the chances that we'll see different results in different execution generally increase. Let us take a look at a Python program that uses scikit-learn to apply k-means clustering algorithm. At first, we import the k-means class from scikit-learn. I will create a two-dimensional list to hold a two-dimensional dataset that we are already familiar with. My data contains all the 9 rows of our dataset. Now we call the fit function of the k-means class with number of clusters equals 2. We provide our dataset, which is stored in the variable myData, as a parameter of the fit function. The function returns an estimator km, which contains all the outcome after executing k-means clustering. The final assignments are stored in this variable named km.labels_. The word label is sometimes used to refer to assignments or cluster membership. We print labels. We should find the cluster assignments for each of the 9 rows of our dataset. The fit method will also prepare the final centroids, for which the result was optimal. km.clusterCenters will give us the centroids. Scikit-learn's k-means implementation also provides the sum of squared distance between each point and the cluster centroid the point belongs to, summed over all the points in the dataset. The sum of squared distance is termed as inertia. km.inertia will give us the sum of squared distance for the final centroids. Let us run the program. Here is the output. Notice that the k-means assignments are numbers. km.labels provided us 9 numbers for the 9 rows of the given data. Based on the outcome, this row at the top belongs to cluster 0. The next row belongs to cluster 0. The next row belongs to cluster 1. The next one belongs to cluster 1, so and so forth. We only have cluster 0 and cluster 1, these two cluster IDs, because we asked for 2 clusters. Chem.clusterCenters printed the cluster centroids. Since our dataset has 2 features, each of the cluster centroids will also have 2 features. These are the 2 centroids of 2 clusters. This is the centroid for cluster 0. This is the centroid for cluster 1. Cluster 0 has 2 features. Also, cluster 1 has 2 features. km.inertia provided the sum of squared distance between each point and the centroid of the cluster that is hosting the point, summed over all the points. The sum of squared distance here is 21.15. One can run the same program multiple times to see if k-means algorithm provides a smaller sum of squared distance. Smaller sum of squared distance would refer to a better and more local clusters, where points are closer to the centroids. One might ask, how can we read data from a file? let us say a CSV file, and then apply k-means clustering algorithm to that dataset. Let us say that we have a file containing 4 columns in each row being separated by tabs. The name of the file here is the data.txt. This file has 150 rows. We will cluster these rows. That is, using k-means clustering algorithm, we will find which cluster each row belongs to. Let us delete the previous dataset because we will retrieve our data table from the file the data.txt. There is a library just for that. The library is called pandas. We will import pandas as PD. We will call the function readCSV from pandas to read our file, the data.txt. The delimiter or the separator between columns is tab. We do not have any header row in our data file. That is, we do not have any name for columns in our file. So we set header equals none. As a result, the readCSV function will use all the 150 lines for the construction of the dataset. readCSV will return a data frame, which contains the data table and additional information about that table. From the data frame, we retrieve the actual data table part using values. The data frame.values will return the data in a NumPy array. After we get the values, my data will contain the actual data with 150 rows and 4 columns. The k-means function is able to use this NumPy array containing our data retrieved from the file. After running this code, we see that our cluster assignment vector has 150 cluster assignments for 150 rows of our data table. We only have zeros and ones here because we asked for 2 clusters. We have 2 centroids. This is the centroid for cluster 0. This is the centroid for cluster 1. Notice that each centroid has 4 numbers inside. That is, the centroids are 4-dimensional. Each centroid has 4 features. The centroids have 4 features because our dataset has 4 features or 4 columns. Here is the sum of squared distance. Let us change the number of clusters to 3 in our code. With 3 clusters, we have cluster 0, cluster 1, and cluster 2. Therefore, this assignment vector has only 0, 1, and 2's. Again, the 150 numbers here correspond to 150 rows of the data. Since we asked for 3 clusters, we have 3 centroids. Each centroid has 4 numbers in them because we have 4 features in the data. Remember, a centroid is the average of each feature of the points in the cluster the centroid is representing. Here is the sum of the squared distance. We can run the program with the same data and the same number of clusters multiple times to check if we receive a smaller and hence better sum of squared distance. The clustering result with a smaller sum of squared distance should be better. Let us quickly talk about the time complexity of the k-means clustering algorithm. The time complexity of the k-means clustering algorithm is known to be big O of number of data points times number of clusters times number of features in data times number of iterations of the algorithm. For datasets with good structures, generally the algorithm converges pretty quickly. That is, there will be a small number of iterations. In practice, k-means algorithm is a quite fast algorithm. I would say that it is one of the most widely used algorithms in the field of data science. It is widely used for exploratory analysis. Let us talk about some advantages of k-means clustering algorithm. The algorithm works well on big data. The algorithm scales well with large data sets. Its quick convergence tendency has made the algorithm quite popular in many disciplines. Implementation of the k-means clustering algorithm is simple. Most popular data science programming tools such as Python, MATLAB, and R already have packages for k-means clustering algorithm, of course, along with many other algorithms. Let us now talk about a few limitations of the k-means clustering algorithm. Clustering data with varying density and size may be problematic with k-means clustering. Clusters in the data may vary in density and size. K-means cannot handle datasets containing structures with too many different sizes and density. For density-driven datasets, we will discuss another algorithm called dbscan in a future video. K-means clustering algorithm can only deal with numerical data. As we have seen in this video, K-means clustering algorithm computes centroids, for which only numerical data is appropriate. Categorical data or string data will need to be converted to numerical tabular data to be used by the K-means clustering algorithm. Figuring out the correct K might be problematic. For two-dimensional or three-dimensional data, we can visualize, but for higher dimensional data, figuring out an appropriate number of cluster can be cumbersome. The K-means clustering algorithm is affected by outliers. If there are outliers in the data, then the centroids of the algorithm can be displaced to locations where the clustering results might not be that good. Even a few outliers can move the centroids away from the regions with clustered points. The K-means clustering algorithm might not return the best solution because it depends on the initialization. As we know, the K-means clustering algorithm starts from a random initialization and searches for a local optima. The best solution is not guaranteed by K-means clustering algorithm. Of course, one can run the K-means clustering algorithm multiple times for a better solution. K-means clustering algorithm is quite popular for its availability with tools, its simplicity, and runtime efficiency. With every clustering algorithm, there is always a question: how good the clustering results are. After discussing a few more clustering algorithms, we will discuss the techniques to evaluate clustering outcomes. Please subscribe to this YouTube channel and hit the bell-shaped icon to make sure that you receive notifications when we upload any new videos. Thank you for watching. I will come back with another video and I will see you there. Meantime, happy learning!